So hi everyone, welcome to the seminar. So it's my pleasure to introduce Tien Tien Yu from the University of Oregon. People who have worked on anything to do with direct detection and of dark matter, particularly involving electron recoils, will know Tien Tien's work. So Tien has done a lot of work with Ruben Essig and people like that on these like semiconductor experiments. But today she's going to be talking to us about not dark matter, but important consideration in this field, which is solar neutrinos. So thank you very much for being with us virtually, and I'll leave it in your hands.
Great. Yeah, so thank you for the invitation. And again, apologies for getting the date wrong. You said March 16th, 11 a.m. So I should have remembered that means it's March 15th for me. So again, thank you all for your patience and your understanding. So like Kieran said, I'm going to talk to you all today about some work on thinking about solar neutrinos in these low threshold dark matter detectors that I've been working quite a lot on. And in particular, when I think about solar neutrinos in kind of two acts, first, I'm going to talk about them as being a background to these dark matter searches that Kieran mentioned that I've been quite involved in. But then also to understand how we can use these same experiments to learn more about the properties of neutrinos. And so this talk is based on two papers. One is one that I wrote a while ago with Ruben Essig and his student at the time, Mukul Shulapurkar, who's currently a postdoc at UC San Diego. And another paper that came out last year with my graduate student, Tom Schwemberger, here at University of Oregon. Okay, so to kind of set the stage, I wanted to start talking about first the dark matter searches. So in particular, dark matter electron scattering. And so when we talk about dark matter electron scattering, when we're oftentimes thinking about sub-GeV dark matter. So what I mean by sub-GeV dark matter is a very specific kind of mass range. So I'll stop at kV scale to GeV. So it's a fairly narrow range in dark matter parameter space. And what I'm showing you here are kind of two classic plots in the dark matter electron scattering world. So on the left-hand side here, or in both figures, the axes are the same. The x-axis is the dark matter mass, and you'll notice that the units of the dark matter mass are in MeV, so that we have 1 GeV on the right-hand side and 1 MeV more towards the left here and here. The y-axis is a sigma E bar, which is a reference cross-section for the dark matter electron scattering. It's a reference cross-section, meaning that this cross-section is calculated at a fixed momentum. And in particular, we often use a momentum of alpha ME, alpha being the fine structure constant, ME being the electron mass, because this is a typical momentum transfer in these processes. And by writing this in terms of this reference cross-section, then we can make these somewhat model independent by putting all the model dependence into the momentum dependence of the scattering. So for example, on the left-hand side, I have this FDM equals to 1. So this corresponds to scatterings that are like a contact interaction or with a heavy mediator, where whatever particle is mediating the interaction between the dark matter and the electron has a mass heavier than the momentum scale, heavier than alpha ME, which is. Whereas on the right-hand side, we have the other extreme where FDM goes like 1 over q squared. And this would correspond to the scenario where the mass of the mediator is much lighter than the momentum transfer, and that this kind of acts like a long-range interaction. Okay. So as Kieran mentioned, there's been quite a lot of activity in looking for dark matter electron scattering in the last several years. And it kind of all really started to percolate in in 2013, about 10 years ago. So in 2018, this was the landscape of the dark matter electron scattering. There's in fact one line that's missing here that I forgot to update. That's a solar reflection line from the xenon experiments. But the point being is that in 2018, all of the limits looking for dark matter electron scattering were from these noble liquid detectors. And it was recasting the results of these noble liquid detectors. Move on to 2021. There's been a couple of updates since then, because now we're in 2023. And this was the landscape, just a few years later. And the point being is with kind of showing these two plots side by side, or these two slides side by side, is that there's been a huge increase in activity in this realm of sub-GeV dark matter detection. And just like full disclosure, I'm a part of the Sensei experiment. So I grabbed the figure from the Sensei paper, and these are our results from 2020 Sensei at Minos, which is the first dedicated experiment to look for sub-GeV dark matter. But you can see there's quite a few other players. So in addition to the noble liquid detectors from the previous slide, so here's xenon 10, xenon 100, and dark side 50. And here you go. Here's the solar reflection line that I forgot to put on the previous slide. There's also been kind of entrance of experiments like Edelweiss, Super CDMS, and DAMIC at Snow Lab. Okay. And looking forward into the future, kind of what can we expect to see? So in particular, just focusing on Skipper CCD, silicon Skipper CCD experiment. So this is the technology that Sensei uses. This is what we expect to see in the next several years, a decade or so. So in particular, Sensei, our plan with Sensei is to get to 100 gram years of exposure. So getting to this cyan colored line here. And where you can see this starts to get quite exciting because we're hitting these beige regions, which are labeled key milestones. These are interesting regions for theoretical target regions where clever folks have come up with models to kind of populate this regime to give you the observed relic abundance of dark matter. There's an experiment called DAMIC-M, which is proposing to get to a kilogram year of exposure. So you can see that their projections are shown here in red. And in fact, DAMIC-M had recently, just maybe a month ago, had their first results out with a much smaller exposure than 1 kilogram year. And then the ultimate goal is for the whole kind of Skipper CCD community to join forces into a collaboration called Oscura. So Oscura is currently funded for R&D. And the goal of Oscura is to get to 30 kilogram years, so to get down to this blue line here. Okay. These same experiments can not only look for dark matter electron scattering, but they're also good for looking at dark photon dark matter. So here I'm talking about the dark photon, which I think many of you are very familiar with, and many of you are very instrumental in kind of pushing it into the realm of being studied. In this case, the dark photon is the dark matter. So what you'll see here is the x-axis is the dark photon mass. And now we're in this like EV scale. So here's 10 EV. So it's much smaller in mass than what I was showing before. Whereas the y-axis is epsilon, which is the kinetic mixing parameter, which tells you the strength at which the dark photon couples to charged particles, charged center model particles. So you can also detect with these same experiments that I was showing in the previous slide, this dark photon dark matter. And so basically you see kind of the same names appearing, just reinterpreting the data in terms of this dark photon dark matter. And you get limits that look like this. And again, what can we expect in the next decade or so would be experiments that like Sensei, DAMIC-M, and Oscura is to get this type of reach shown in this figure. Okay, so as we see, there's been quite a lot of activity. There will be continued activity. And so as these efforts start to grow and increase in exposure, you might start to worry about things like backgrounds. In fact, you were already worried about backgrounds, but you might ask what other backgrounds do we need to start worrying about? And specifically, the background that one might start to worry about is the background coming from neutrinos. So for the kind of the connoisseurs of dark matter direct detection, you're familiar with this idea of the neutrino fog, which used to be called the neutrino floor, which for WIMP dark matter searches kind of signaled where you started to start to see neutrinos mimicking your dark matter signal. And once you reach this point, you need to kind of be a little more sophisticated in your analysis if you wanted to discover dark matter. So to kind of start this conversation and this discussion, I want to first remind you of what the neutrino fog, is rebranded as neutrino fog, looks like for dark matter nuclear scattering experiments. So just to kind of remind you all, how does direct detection work? So when we have a direct detection experiment, what you're looking for is the dark matter, which is floating around in our galactic halo with some kind of velocity dispersion that is periodically passing through the Earth. On Earth, you have your detector, here denoted as a blue box made of some target, which is composed of atoms. And you usually have this box of material somewhere deep underground, and you look for the interaction of this dark matter scattering off of the nucleus. Through this scattering, the dark matter transfers some energy, momentum, to the nucleus, causing the nucleus to recoil. And therefore, the signal that you look for is this nuclear recoil signal, this jiggle of the nucleus. So this has been this kind of basic idea of looking for dark matter has led to a very clear program that has kind of guided the dark matter direct detection searches for the last several decades. And so it's led to something that looks like this. So again, this plot is also a little bit out of date because LZ now has a new result. So what I'm showing you here on the x-axis is the dark matter mass. You'll notice here the dark matter mass is in GeV. So not MeV like we had before, but in GeV. So this is like classic WIMP territory. And the y-axis is the dark matter nucleon cross-section. Okay, and you'll notice these numbers are actually quite a bit smaller than they were for the dark matter electron scattering case. And so this idea of looking for dark matter nuclear scattering has led to beautiful results from the xenon collaboration and from LZ and from Pandax, from many different collaborations, to exclude quite a bit of this parameter space. So all this parameter space in blue has been excluded. LZ sets slightly stronger limits than this. And so we're clearly marching on down in kind of this WIMP parameter space. Okay, so the other thing that's being shown in this figure is this orange region, which I've labeled the neutrino background. And so that's kind of the focus of what I wanted to talk about. So you can ask, what is this neutrino background? So neutrino background, as I said earlier, is when the neutrinos, which also scatter off the nuclei, start to mimic your dark matter signal. So these are the cross sections at which you start becoming sensitive to these neutrinos. So you can ask, what are these neutrinos? Where are they coming from? Well, there's a few sources. When we're up here at the higher masses, so therefore corresponding to higher energies for the neutrinos, these are coming from atmospheric and like the diffuse supernova background for neutrinos. So these are what populate this part of the plot. When we go down to lower masses, you get this kind of cliff, this little bump, whatever you want to call it, which is coming from the solar neutrinos. And in particular, this bump right here is from the boron 8 neutrinos. Okay, so you can ask, how exactly do these neutrinos contribute to, how do they mimic the dark matter signal? Okay, so again, remember that basic idea of direct detection is you have your detector with your nucleus just hanging out. The dark matter scatters off the nucleus and the nucleus jiggles. So the neutrino background is calculated when rather than a dark matter coming in, you have a neutrino coming in, and the neutrino is the thing that scatters off of the nucleus. Okay? And the nucleus therefore jiggles. And in fact, we know that this process has to happen because the neutrino nuclear scattering is a standard model process. It's known as SEVNS, which is the coherent elastic neutrino nuclear scattering. And this gives us this neutrino background. Okay, so let's look at SEVNS. So what exactly is going on in SEVNS? Should be elastic here, apologies for that. So we have the neutrino that's scattering off of nuclei through an exchange of the weak interaction, so exchange of a Z boson. And this gives you a scattering cross-section given by the following expression. So you can see here, as a function of the nuclear recoil energy, it depends on the neutrino energy, as well as the atomic mass and number of the target. Okay, so SEVNS, like I said, we expect this to happen. This is a standard model process, and indeed, we saw evidence for SEVNS in 2017. So this is a figure that I took from the science paper from the Coherent collaboration. So in 2017, they demonstrated the first observation of SEVNS. So what I'm showing here is in the top axis is the counts per number of photoelectrons. So we have counts on the y-axis for photoelectrons. And the left panel is showing when the beam, so coherent is next to a neutrino source. When the beam is off, you don't see any kind of excess counts. But then when they turn the beam on, you see this beautiful peak in the number of photoelectrons. Similarly, you can plot this in terms of the arrival time. And again, when the beam is off, you see no increase in the number of counts. Whereas when you turn the beam on, you get this beautiful spike in the number of counts. Okay. Okay, so how does this relate to dark matter? So to relate to dark matter, let's go back to calculating the scattering rate for sevens. So again, what goes into the scattering rate of sevens? Well, you have the cross section, which is the expression we saw before. And then you need to convolve this cross section with the flux of the neutrinos, which is this, if you guys can see my mouse, is this dn nu de nu. You integrate it over the neutrino energies to which you're sensitive to, which depends on your detector threshold. You multiply it by your target mass, the amount of time, by the exposure and the number of targets. And from this, you get the number of events you would expect per unit of time, per unit mass. Okay, so this is very well predicted in the standard model. So you can see a key thing to calculate this rate is this piece here, the neutrino flux. Okay, so again, what is contributing to the neutrino flux? So in the dark matter detectors experiments, the thing that's contributing to this dnu dnu are exactly these neutrinos. So at the higher masses, they're the atmospheric and supernova neutrinos, whereas the lower masses, they are the solar neutrinos. Okay, and so we can see we've already kind of started to touch the solar neutrinos. So this is where I'm going to focus my attention. Okay, so let's look at solar neutrinos. So here's the sun. It's producing neutrinos through various nuclear processes. These neutrinos exit the sun and come towards the Earth, which is shown here. And then you can plot the flux of these neutrinos as a function of neutrino energy, which I've shown here. This is a very specific solar model that I'm showing you here. And you can see that there's these various components of neutrinos. So here's the boron-8 one that I mentioned earlier. Here's the PEP neutrinos, the beryllium-7 neutrinos. There's two lines here. The CNO cycle, which are labeled NOF here. So basically, depending on what nuclear process is creating the neutrinos, this gives you a different flux of the neutrinos. So the components that contribute to our background are the ones that are shown in colors here. So boron-8, PEP, beryllium-7A, and the CNO, the neutrinos. Okay. So once I have the neutrino flux, then I can start to calculate the rate at which I see neutrino nuclear scattering. Okay, so I plug that flux into here. I plug this expression of the cross section into here, and then I can start to calculate the rate as a function of the nuclear recoil energy. So if you go and do that exercise, you end up with a figure that looks like the following. So this is the solar neutrino rate in silicon. I'm showing you here silicon. And you can see the different components of the solar neutrinos. So in particular here in red, the red dash is the boron-8. We have the CNO, which is here O and F. Those guys here. And the total contribution of these neutrinos is given by this black line. Okay. There's a few other kind of things that are being shown here, like this high fiducial low. I mean, I'll reserve conversation about those to a little bit later, because I'll explain what I mean by those in a few slides. Okay, so once you have this rate, which is the number of events you would expect to see from neutrinos as a function of the nuclear recoil energy, you can start to calculate the neutrino background by comparing the dark matter spectrum, which is also gives you a predicted number of events per nuclear recoil energy. You compare that to the neutrino background, and then you would calculate at what cross section does the dark matter prediction match the neutrino prediction. And through that process, then you get this orange curve here. Okay. So for each dark matter mass, you get a predicted scattering rate. And this rate can be normalized with the cross section, and you find at what cross section does it match the neutrino prediction. And that's what determines this line here. Okay. So far I've told you the story and kind of how we calculate the neutrino background in dark matter nuclear scattering. But you might say, I started this talk focusing on these low threshold detectors, which are looking for an electron signal, not a nuclear signal. So how does this relate to those experiments? Okay, how does this relate to dark matter electron scattering experiments? So it turns out that if you have some nuclear recoil energy in your detector, this will also induce an electron recoil signal, meaning that even though the interaction of the neutrino is with the nucleus, and it's the nucleus that's recoiling, the recoil of this nucleus will induce an electron recoil signal. And it's this electron recoil signal that the experiments I was discussing at the beginning of this talk are sensitive to. And so in this way, you also get a neutrino background for these electron detectors, for these low threshold detectors. Okay. And so how do we calculate this? So this efficiency, what we need to then calculate is the efficiency of translating this nuclear recoil energy into electron recoil energy. So one of the kind of classic ways of doing this is through what's known as the Linhart model. So what the Linhart model tells us is it gives us this ionization efficiency, which in this top line here I have indicated as Y. And this ionization efficiency tells me, given a certain amount of nuclear recoil energy, ENR, how much electron recoil energy do I get out of it? And the Linhart model tells me that this Y, it's kind of empirically determined, is given by this expression here. And you can see that this Linhart model depends on properties of the nucleus that you're scattering off of. In particular, it depends on Z. Okay. There's been, so there's actually quite large uncertainties in here. And we usually treat this K as a free parameter. So you'll see in the next few slides some choices that we've made for K. Okay, but so this Linhart model has worked quite well when nuclear recoil energies are high. So when you're above a few keV. So what I'm showing you here is the ionization efficiency in germanium. So here's germanium. And you can see in green are some data points taken from a variety of different experiments, and that the lines are the Linhart fit. And you see that the lines fit quite well for germanium, but we run out of data at 200 eV. So to go below 200 eV, we then extrapolate this Linhart model. And so to do this extrapolation, we make kind of three hypotheses, which we call the high, fiducial, and low models, which basically correspond to at what energy do I assume that the efficiency goes to zero. Okay, so for the high efficiency model, I have the lowest cut. So in the sense, it's high because it's the most efficient ionization efficiency. You can transfer the most energy out of it, whereas the low has the higher energy cut. So you're the least efficient at translating this energy. Okay, so here I have the nuclear recoil energy on the x-axis and the electron energy on the y-axis. And you can translate the electron energy into number of electrons. So 10 electrons corresponds to this horizontal line here. So you can see Linhart works quite well for germanium. And indeed, this high, fiducial, and low that you see in this plot are these lines that I'm showing you in this plot. So now I'm showing germanium, but what these high, fiducial, and low are saying, given a specific ionization yield model, the high, fiducial, or low, these are the energies that I'm sensitive to. So if you take the low model, which would be this line here, you would be sensitive to everything to the right of this. So in effect, you're only sensitive to the boron 8 neutrinos. However, if you take the high efficiency model, which is this leftmost vertical line, you're sensitive to several more components of the solar neutrino flux. Okay, so that's the story for germanium. That's pretty cool. But the story is not quite as simple for silicon. So in silicon, we have, again, data shown in green, but we also have data shown here in the black dots. And this is data from the DOMIC experiment. And the Linhart model in this plot is shown in red, right? So at high energies, it matches well. But once we get to about kV or so, the Linhart model does not line up with the DOMIC data. So for silicon, we do something a little bit different. We take the Linhart model as our high yield function, so the red line. It's the most optimistic case. For a fiducial one, we do an empirical fit to the DOMIC data. So that's this thing given in the black dashed line. And for our low model, we do a linear fit. So again, this is a log-log plot. We do a linear fit to the dynamic data, and it gives us a conservative limit. So here the E cut is at 300 eV. Okay. So for silicon, then what is the story? If I go back to this recoil, this rate, DRD, differential rate, you see that for the low model, again, you're only sensitive to the boron 8 neutrinos. Fiducial model, you're sensitive to a few more of them. And then the high model, you even start to be sensitive to the beryllium 7 neutrinos. Okay, so you can see there is quite a sensitivity to which ionization yield that you use. And also note here that there's been more recent work backed by Sarkis et al. To come up with a more kind of a more sophisticated modeling of this ionization yield. Okay, so so the reason why I went through that whole story about the ionization yield is because here I have a plot of the recoil rate as a function of nuclear recoil energy. However, what I want to have is a plot or a calculation of the rate as a function of the electron energy. So by taking this ionization yield, I can then convert this, we see the y-axis here, which is the recoil, the rate as a function of nuclear recoil energy, into the rate as a function of electron energy. And so that's what I do here. Here's kind of the formalism that I use. On the left-hand side is the number of events I would expect to see per kilogram per year, so the rate in silicon, using the fiducial model. And in the the left-hand side is silicon, and the right-hand side is the same thing, but for germanium. And now instead of writing in terms of electron energy, I've written in terms of the number of electrons that you detect. Okay? There's a way to map between these two. And so what you see is if you have sensitivity to one electron, so this is this first bin, you have sensitivity to several of these neutrino components. So you see several colorful lines here. When you go to the 2 electron threshold, you would be sensitive to these guys here. But once you go above that, you basically are only sensitive to the boron 8 neutrinos. Okay, so at high energies, you only have boron 8 guys. So going back to the earlier plot, which was showing the flux of solar neutrinos as a function of neutrino energy, we can now convert these sensitivities with 1, 2, and 3 electron thresholds to neutrino energy. So let's focus on the top here. So this is showing silicon for the 3 different ionization models. So I have the high yield model in red, the fiducial model in black, and the low yield model in blue. And the different horizontal lines are for 1 electron, 2 electron, and 3 electron. So again, as you would expect, the high yield means you're sensitive down to the lowest neutrino energies. And you see that also for silicon, you can get down to the lowest energies compared to germanium and xenon. Okay, so this was quite a long prologue to now really getting into how these solar neutrinos affect our experiments, these low threshold experiments. Okay, so let's start with Act 1. So Act 1 is where my goal, I have my dark matter hat on. My goal is to look for dark matter. And in this case, these neutrinos are a background. They're not what I'm interested in. I'm interested in dark matter, and these neutrinos are kind of getting in my way. And so again, we do something similar to what we did in the nuclear case, which is to compare the dark matter spectrum to the neutrino spectrum. So again, there's kind of 2 processes going on here. We have scattering. This is dark matter electron scattering. This is what I'm showing on the left. And we have absorption, which is like this dark photon absorption, which is what I'm showing on the right. In both plots, the dashed lines, so in the absorption, it's this peak here, labeled 200 eV. And in the scattering plot, it's these three different colors, purple, orange, and green. These are the dark matter signal, okay, for different dark matter masses. And in the solid colored lines are the neutrino spectra for the 3 different ionization yield function hypotheses. So what we then do is we want to compare these two spectrum. Okay? And the question in particular is, there's some uncertainty that's involved in these in the neutrino spectra based on the uncertainties in the neutrino flux. So the question is, how much dark matter can I hide in in this spectrum. And so to make this comparison, you need to define a measure for how well do two spectra fit. And to do this, we use a log likelihood analysis. So what we do is we compare a background-only hypothesis, saying that there's no dark matter. All we have is neutrinos. So basically, for the scattering case, we're setting the scattering cross-section of dark matter to electrons to 0. And then you float all the neutrino parameters. And you get a test statistic, which then tells you the significance at which you can reject this background-only hypothesis. Okay, and you maximize this over the neutrino flux uncertainties, or you minimize them minus the log of this guy. Okay, so if you go through this process, then you'll end up with figures like this. So this is quite a busy plot, so I'll talk you through what's going on here. So these both are for a heavy mediator in silicon, which is indicated here. And again, it's the dark matter mass and MeV on the x-axis and the dark matter electron scattering reference cross-section on the y-axis. So let's focus. The different colored lines are different exposures. So I have 100 gram years of exposure. So if you recall, this is kind of what we're planning to get to with Sensei. We have a kilogram year of exposure, which is what Dominic M plans to get to, and 10 kilogram years here in green, which is what Oscura, a third of what Oscura plans to get to. So each of these colors actually has kind of three things going on. We have the background-free hypothesis in dashed, which is assuming that there's no neutrinos. And so this would be the naive hypothesis of everything that you see is dark matter. And what you see is that for 100 gram years and a kilogram year, I'm focused on the left-hand plot here, you don't see the dashed line. So what this is telling you is that the background-free hypothesis is a good hypothesis, and that you're not sensitive to the neutrinos quite yet at this case. However, when we go to 10 kilogram years and above, you start to see a difference between the solid line, which is the fiducial yield, and the dashed line, which is the background-free model. So this is telling you now that the solar neutrinos are starting to contribute to your rate. You're starting to become sensitive to them. The bands are indicating the choice of your ionization yield, right, where it spans between the low and the high. So in fact, even at a kilogram year, depending on your ionization yield, you would start to see a difference. Okay. So in particular, kind of the punchline here is 100 gram years, don't need to worry about neutrinos. Kilogram year, maybe you need to start worrying a little bit about neutrinos. 10 kilogram years, you definitely need to think about neutrinos. And the right-hand plot is the same thing, but now showing you two different thresholds. So the dashed line, the dotted line here is the 1 electron threshold, and the solid line is the 2 electron threshold. Okay. And again, the dashed line is the background free, which we only start to see at about 10 kilogram years. This is the background free for the 2 electron case. So this is for the heavy mediator. We can do the same thing for the light mediator with very similar punchlines, which is that for 100 gram years, 100 gram years, solar neutrinos are not a background. You are not sensitive to them. Kilogram year, depending on your ionization yield, you need to start worrying about neutrinos. And at 10 kilogram years, to properly do your constraint or your projections, you do need to include solar neutrinos. Okay. So this was for silicon, which is a semiconductor. You can do the same exercise for xenon, because again, the first limits in kind of this parameter space for these models were from noble liquid detectors. And the story in xenon is a little bit different, because even at 100 gram years, you start to see the neutrinos. Okay? The neutrinos become important sooner for these detectors. Okay? And you definitely start to see a difference at a kilogram year. Okay. And so why is that? Well, the reason for that is because in xenon, the spectrum tends to be flatter. And in fact, it's mostly dominated by the boron 8 across the whole spectrum. And the Simons rate is also larger in xenon because this scales like a squared, right? It's a coherent scattering. Xenon also has a slightly lower ionization efficiency. And so the boron 8 spectrum really coincides very well with the dark matter spectrum across a wide range of masses. and exposures. So for this reason, neutrinos start to become important earlier in xenon and comparably with argon. Okay. So you can kind of plot these results in a slightly different way, which is, so this is for silicon and a heavy meteor, which is the cross-section reach as a function of the exposure for two different, so here I'm showing two different masses. I have half an MeV in blue and 10 MeV in orange. The background free hypothesis is given again in the dashed line here and here, whereas including the neutrinos is shown in the band. So again, we see that at 100 gram years to even a kilogram year, the neutrinos you don't really see a difference between the dashed and the solid lines, which is telling you the neutrinos are, you don't need to worry about them quite yet. But as you increase in exposure, you start to see a difference. So one key thing here is that there's no floor per se. You don't see these lines flattening out. They slow down, but they don't flatten out. So the reach with the exposure will slow down, but doesn't plateau. So there's no like proper neutrino floor for this. Okay, so this is this case for dark matter electron scattering. The other kind of model that I had discussed was absorption, and now I've added a bonus one. So the right-hand side is the dark photon absorption, so epsilon versus mass of the dark photon at the right-hand side, and the left-hand side is axions, ALPS, and it's the axion-electron coupling in particular. Okay, so a question? Okay. And here, again, kind of the color scheme is the same, and the line style is the same. So let me focus on the right-hand plot. What we see here is that for kind of the majority of the range, that the solar neutrinos actually don't really come into play until you get to like 100 kilogram years. And the reason for this is because at the high masses, the ionization efficiency and the yield data constrain the efficiency, so there's less uncertainty here. And as the dark matter mass increases, the neutrino background, again, is dominated by the boron 8 component. And so at these higher masses, this effectively remains a background-free experiment. Whereas at the lower masses, the neutrinos contribute more. So we see this story kind of appearing with the bands appearing at the lower masses and disappearing at the high masses, and that the solid line and the dashed line remain pretty degenerate until we get to high exposures. Okay. So that's the story for silicon. I can show you the same plot for xenon. Kind of similar punchlines as with the scattering case, which is that the neutrinos start to contribute earlier than in the semiconductor case. So we see that here at 10 kilogram years and 1 kilogram year, you already start to see the neutrinos. Okay. So just to kind of summarize this part, because that was a lot of information. So the takeaway for neutrinos as a background is that solar neutrinos are an important background for dark matter electron scattering when you start to get to exposures above a kilogram year. But they're already important in xenon at 100 gram years, and like these detectors are at exposures higher than this. So for xenon experiments, you need to fold into the fact that solar neutrinos exist and will be scattering in your detector. For absorption, they start to become important at about a kilogram year of exposure. So for me, as somebody like wearing my sensei hat, is I don't need to worry about solar neutrinos quite yet. But for a Skura, atomic eminence Skura, I do. Okay, so that's solar neutrinos as the background. So now I'm going to kind of switch gears. I'm going to take off my dark matter hat and put on my neutrino hat and think about, let me use this as an advantage. Rather than saying, like neutrinos are getting in the way of me looking for dark matter, I will say, this is a great opportunity to learn more about neutrinos. So what can I learn about neutrinos with these direct detection experiments? Okay. And there's a few reasons why I would want to use direct detection to look for solar neutrinos in particular. One is that you can measure the pure neutral current boron 8 spectrum for the first time. You can calculate, like have a first direct measurement. These are all in principle. You'll see in practice, this is much harder. the first direct measurement of neutrino survival probability in the transition region. You can go to lower energies than existing SNO measurements because we are able to go to such low thresholds, so on and so forth. You can measure survival probability in the vacuum region. So this is a lot of jargon that I'll explain in a bit. And you can help understand the solar abundance problem. And you can study non-standard interactions of neutrinos. So in fact, there's a lot of stuff being shown on the slide, and I'm just going to focus on this last piece in the interest of time. Okay, so what do I mean by non-standard interactions of neutrinos? So let's go back to what the standard interaction of the neutrinos is, which is the sevens in direct detection, which again is this neutrinos coherently scattering off of nuclei in your detector. So when I'm talking about non-standard interactions, what I mean is rather than looking at a neutrino going through neutral current scattering off the nuclei, I'm going to replace the Z boson with something else, which could be a vector boson, a scalar, a pseudoscalar axial vector, or I can give the neutrino magnetic moment. And then I specify the coupling of this new mediator to the neutrinos and the coupling to the nuclei. I can also have this guy coupled to electrons as well to get a neutrino electron interaction. Okay, so I know this is not quite the way that non-standard interactions is defined in the community, in the literature. So I'm taking non-standard interactions and taking kind of a simplified models approach to it. Okay, so just to be clear. Okay, so like again we can also look for electrons here. Okay, so once I have these non-standard interactions, let me I can pick some kind of Lorentz structure for my mediator, and I pick the couplings. I can look at the recoil spectra for these guys. So this is in silicon, the recoil spectra for a few of these new interactions given in these colorful lines. So there's quite a lot going on here. The black line, which is a little bit hard to see, which is shown here, is the standard model prediction for the rate as a function of recoil energy. And these color lines are for different non-standard interactions. So the blue lines are for a vector mediator. The orange lines, which are shown here, for a scalar mediator, and the green line, which is hidden underneath everybody else, is given in is given here as a magnetic moment interaction. And then the dots, so these red dots and this blue and orange, purple dots are experimental constraints. Okay. So with this simplified kind of models approach, we can, so there's a few things. One, you notice that these rates all increase, or most of them increase with as you go lower in energy. So the reason why I got interested thinking about neutrinos is because we now have these experiments that are sensitive to EV scale energy depositions, then we have access to all of these events if they existed. Okay. So I can do a similar exercise, which is to plot the event rate as a function of the number of observed electrons in terms of these simplified models. So what I'm showing on this panel are each box is a different element, a different target material. So let's focus on the top left one, on silicon. The rest are basically, the content is similar. The black line is the standard model prediction. And the band is given these different ionization yields, right? So you can see at high energies, there's no uncertainty in the yields. At low energies, it really depends on our choice of the yields. You get this big band. And then the blue and the red are for the non-standard interaction. So in this particular example, I take a vector mediator with 100 EV in mass, and I fix the couplings to these numbers in the legend. So the red line is the nuclear recoil. And again, you see that there's this uncertainty band because I need to translate this nuclear recoil energy into electron recoil energy, which then translates to the number of electrons. And the blue is the electron recoil, just neutrinos scattering off of electrons. And there's kind of a few cool features here, in particular with the nuclear recoil case, because you get this interesting interference effect between the standard model and the NSI, and you get like a little dip here. So if you were able to measure out to these energies, you could look for this dip as a handle to differentiate between some new mediator existing and in the standard model case. So now you can compare or make projections for what kinds of constraints or sensitivities would you have to these non-standard interaction parameters, which is the mediator mass and the couplings of the mediator in these various experiments. So I can project these sensitivities. So again, these are showing you 3 different targets. Here's silicon on the left side, germanium in the middle, and gallium arsenide. So these are all semiconductor experiments. On the right-hand side, the top panel is for electron scattering, so the electron coupling, whereas the bottom panel is for quark coupling, so nuclear scattering. So here's a projection that we made for the Sensei Minos data. It's up way up here. So here's xenon. So not saying anything super exciting, but there you go. There they are. Here's Edelweiss. But if you think forward to the future for Sensei, Dynamicam, and Oscura, you could expect to get sensitivities as shown in these blue lines. So the solid colored line is assuming a 1 electron threshold, and the dashed line is with a 2 electron threshold. And so this is kind of exciting because you're starting to probe new parameter space that was not probed by these other experiments shown on the plot. The story is even more exciting. So this is for the semiconductor experiments. The story is even more exciting for the noble liquid detectors. So here is xenon on the left-hand side and argon on the right-hand side. It's partly exciting. 10 years rather than kilogram years of exposure. And you can see that you really start to carve away in this parameter space. So this is for the vector. You could show similar plots for the other mediators. But the vector is particularly interesting because then you can start to map these simplified models onto a more UV complete model. And so kind of a favorite of folks would be the B-L model. So again, this is quite a busy figure. So I'll explain. So what we have here is the mass of the B-L vector boson on the x-axis in MeV. And on the y-axis is the gauge coupling of this guy. So what's shown here are several different constraints. The constraints shown in blue, the shaded blue regions, are ones that are sensitive to the electron couplings. So the B-L boson coupling to electrons. The gray regions shown here with the B factories and here with the beam dump require both electron and nuclear couplings, whereas the red regions are for either one. So you can see there's quite a lot of stuff that's been covered in this parameter space. And these dark matter direct detection experiments would give you sensitivities given in the colorful lines here. So which is to say, like, they're not amazing. In fact, there's this little gap here that is probably actually ruled out by BBN. One of the graduate students here is working through this a little more carefully. So I got excited about this at first, and I think it's not actually there. But maybe here you can start to say something new. Okay, so that's for these vector bosons. You can also ask, let's look at another model. Let's look at the neutrino magnetic moment. And the question you can ask here is, at what exposure would you need to start to have sensitivity to a neutrino magnetic moment comparable to the current limit? And so this current limit I'm showing you here is 2.8 times 10 to the minus 11. The Bohr magneton is coming from xenon, I believe. And to have sensitivity to a neutrino magnetic moment of this size, you would need the following exposure. So silicon is shown here in red, and gallium arsenide and germanium are in yellow and blue respectively, and xenon is shown in this dark green. And we really highlighted here the 30 kilogram years, which is the anticipated exposure of Oscura. And you can see that Oscura can start to, which is silicon, can start to detect this at a more than kind of 2 sigma level, in fact, at 3 sigma. So that's kind of exciting because these experiments were not built to look for neutrinos, but you can do some interesting physics with them anyway. Okay, so I'm kind of keeping an eye on time. So I might skip over a few things and go to the punchline. So maybe I'll go to this punchline. So I had a bunch of other stuff listed in the kind of interesting physics you could learn about neutrinos with direct detection. And so kind of the takeaways from that, because it'll take me more than 10 minutes to go through that, is that in principle, if you combine these experiments with works, you can start to probe some interesting properties of neutrinos, and in particular, what's known as the transition region for the neutrino oscillation. And that you can start to detect additional components of the solar neutrinos, and specifically the PEP and beryllium-7 neutrinos with exposures that are reasonable, 10 kilogram years of exposure. So these two get a smiley face. However, if you look at this one, so the detection of PEP and beryllium-7 neutrinos, and you look at what kind of uncertainties can you measure these with, these are with really large fractional uncertainties. So even if you see them, you can't measure them precisely enough to really say anything meaningful. Similarly, with the CNO cycle, if you go to quite large exposures, 100 kilogram years of exposure, you can start to detect the CNO neutrinos. So that gets a smiley face here. But again, with very large fractional uncertainty, so frowny face. And as a result, you don't really, you can't really say anything too meaningful with that. Okay. All right, so let me conclude. So again, thanks for all your attention. So I kind of motivated this talk by talking about all these different low threshold direct detection experiments that are coming online, the fact that there's a lot of activity going on in this field. And as these experiments start to increase in exposure, the coherent scattering of neutrinos, solar neutrinos, become an important part of these experiments. And we really need to start making sure that we incorporate them into our analyses. So what we learned was that the solar neutrinos become a source of background at about a kilogram year for both scattering and absorption in these elements. So scattering for the semiconductor experiments and absorption for semiconductor and the noble liquid experiments, and that they become important even earlier for the xenon experiments and scattering at 100 gram years. But neutrinos are not just a background; they're really interesting in their own right. So you can kind of flip this on its head and say, what can we learn about neutrinos with these experiments? And what we found is that you can significantly, you can define significantly as you wish. You can improve on non-standard interactions constraints of neutrinos with these next generation experiments. You can start to probe new parameter space. You can measure the neutrino survival probability over a wide range of energies, but to resolve things like the solar abundance problem, which requires measuring the CNO abundance fluxes more precisely, requires exposures well beyond what we can expect to see in, at least probably in my lifetime. Okay, so I'll stop here and take any questions if you have them.
Great, thank you very much for that talk. Yeah, let's have some questions from the audience. You can just go ahead. If not, I'll ask first. So can I ask a bit about the way you modeled the signal for the xenon case, because you were using the same, this is sort of analogous type of signal in terms of like individual electron numbers. But
yeah,
as I know, xenon tend to, they when they show their signals, they talk about like S1 and S2. Do these easily map onto that in the xenon case?
Yeah, let's see. Actually, did I show a flux? Yes, indeed, for the xenon case, I was a little bit quick here. What you would need to map these onto are photoelectrons, right? Which is what the experiments give you. So there's actually one additional step to go through. And indeed, we do that. In the paper I did with my student Tom Schwimberger, we also use a slightly different ionization yield model. We use the NEST modeling. So he went through and looked up the data from NEST and used that. So we kind of did a slightly more sophisticated analysis, but in this case, indeed, I think for this particular paper, we stuck with the number of electrons. But if you wanted to, let's say, recast xenon 1 ton S2 only data, you would need to take that additional step to translate this axis into photoelectrons.
Yeah, and I guess by plotting them on the same plot like this, you're kind of implicitly assuming that you've got no like electron nuclear discrimination.
Yeah. In fact, so that's kind of the maybe the trade-off with going to these electron recoil experiments is you lose that handle.
But will that start to come in? Like, at what value of like any would you need before, like in xenon, you could start to tell the difference, or indeed in the other experiments?
Yeah, so I think the okay, I'm can maybe speak more clearly with silicon. In silicon, there are events in the 1 electron bin. So it would be nice to have some additional handle there, but we don't. However, once you get to like 2 electrons and above, it's actually a like for Sensei, we're actually background free. So in that sense, you don't need that additional discriminating power because you don't expect to see anything that's not dark matter. But yeah, for the 1 electron case, I don't know if you ever could differentiate between the
but
two.
If you go up to like hundreds or 200s of electrons, presumably then you're starting to
because you would get a prediction of what it would look like from nuclear scattering to get that number of electrons, and a slightly different model that would give you the same with just a pure electron scattering. I guess if you could measure the spectrum, I guess that would give you some discriminating power.
I also had a question about the there was a plot where you were showing some possible constraints, and you were comparing like xenon and argon side by side. I think it was like GVGA constraints.
Yeah, let's see. This one.
Yeah, I was just a bit.
Xenon and argon.
Yeah, a bit puzzled because it looked like argon actually does slightly better than xenon here. Is there what is the underlying event in this
so
case?
the exposures are not the exposures are not exactly the same. The solid line is the same. Is that right? Yeah, the solid line is both 1,010 years, but the other colored lines are the exposures for argon are slightly higher. Because my understanding is it's easier to get more argon than xenon. So this is the story that the experimentals.
But I guess even for the same exposure, are these like electron events that are going into?
So the top panel is for electron events, and the bottom one is for nuclear events.
Because I would have thought
that have been translated into electron events.
The argon would be suppressed by like the ratio of the neutron number squared for like the nuclear recoils. But
I think because in both these, in the nuclear recoil case, you still need to translate that into electron energy.
Okay.
So there's an additional step folded in there. Because indeed, naively you would expect this because of this A² enhancement that the xenon would do much better. I believe with from NEST, somehow argon is more efficient at translating this energy into electrons. So they're quite comparable.
Sorry, maybe I'll let somebody else ask a question if they have anything. If not, I can keep going. So I also want to know about the background, like other backgrounds in these cases. Like, what are the backgrounds like when you're dealing with like 1 electron to 4 electron in like these xenon argon experiments? Like how well?
Yeah, so I would say the 1 electron case is not super realistic because there will probably be backgrounds like now, right? The experiments are seeing quite a lot of events in the 1 electron channel, which is why they're not using those to set dark matter like sub-GeV constraints. The 4 electron, I think, is much cleaner. so I think the 4-electron is more or less under control. But there are efforts, at least like in xenon, of people trying to characterize the one electron events. So the hope is that by characterizing these 1-electron events, you can come up with a background model to then subtract.
Yeah.
That you could become a background free. We're not there yet, but that's the goal.
I'll ask a question. Hi, Tien Tien.
Right.
So when you're calculating the neutrino rates in the semiconductors, what sort of approach did you use for that? Or is it assuming anything about the crystal? Like, is it including any of the crystal effects, or is this just?
No, so this is really just the scattering of the neutrino off of the nucleus. So doing like a regular nuclear scattering.
Yeah, and so did you do electron limits? I can't.
Yeah, and so there are electron limits, but here the energies are high enough that I guess what you're kind of getting at is if you need to use something like QE dark or dark alpha,
yeah,
the stuff that we use for the dark matter electron scattering. So the answer is no, because we're in a regime where we don't think we need to do that. There is there might be some smaller effects when you get to the lower energies. So I don't have that plot. Let's see. I think it was in this kind of plot.
Yeah, I guess this was the one.
You would start to see like some steps.
Yeah.
Here. Yeah. In principle, yeah. If you wanted to do it properly. So I think for xenon we did
right.
Try to do a bit of an estimate for those effects, and it didn't affect things by a whole lot.
Okay, thank you.
But yeah, that's a really great point.
I can ask a bit more broadly about like these future semiconductor experiments, like the future Sensei Adamic and then Oscura and all of this. So the sort of projections you showed at the beginning, I think in the case, I think it was the light mediator case where you have this freeze-in model, it kind of almost seemed like it was overkill. Like you're going through the model and then going way past it. But I guess are you also kind of trying to make sure you capture as much of that left-hand one as possible? Is this, I mean, what I'm asking is Oscura kind of the exposure for that kind of experimentally driven or theoretically driven at this point?
I say it's well, I guess the more exposure you get, the more events you would start to see. So even if you're sitting here and you start to see something, if you have such a high exposure, you would get a large number of events, and then you can start to do things like a modulation search where you need statistics to detect things. I guess the paper isn't out yet. There's like also some kind of interesting science that you can do with Oscura that's not dark matter. There's some like military searches that one can do. So in general, like the more exposure, the better. So I agree, like if you were just interested in reaching this line, this is a overkill. But I think to really study what's going on here, if you were to see something, you would need to get exposure as much higher just to have enough statistics to say something more sound.
I guess I'm also curious, I mean, on the experimental side, like how big a jump is it in terms of feasibility from going from 1 kilogram a year to 30 kilogram a year? Is it just a case of getting a bigger semiconductor, or is there?
Yeah, I think it's actually pretty tricky. That's my understanding talking with the experimentalists is there's a few things that are tricky. One is like you could say, oh, well, you just get many more semiconductors and put them together. However, I think there's a challenge with instrumenting them. There's like a limit to the size that you can instrument one. So therefore, it becomes like a multiplexing problem, which is if you have many different readouts, how do you join them all together in a way that doesn't introduce more noise? And I think there's also a challenge of making the wafers larger. So this is kind of what the research, that's the R&D that's going on now, is studying how exactly do we, like I think to get to a kilogram years was not too bad to go from like Sensei to Damacam. That's okay. But this next step, going another order of magnitude, my understanding is it's a bit trickier. it's not just like putting more semiconductors, which is what I naively was thinking.
So anyone left wants to?
I have an elementary question.
Yeah, go ahead.
Okay.
Yeah, for this prospect of new physics from anomalous neutrino magnetic moment, I bet there must be some strong constraint from early universe cosmology, like Big Bang nuclear synthesis.
Yeah, that's a good question.
So my question is,
Okay.
is it constraining different parameter space or the different mass and cross-section range, the magnetic moment range, or is it overlapping with?
I mean, so for the magnetic moment, there's only one free parameter, right? It's just the magnetic moment of the neutrino. Because I think you're thinking in the other cases, there's the mass of the mediator and the couplings of the mediator. The magnetic moment, the reason why we were able to do the study that we did, let me see if I can find the figure. This figure is because there's just one parameter, so we could actually do this likelihood test of it. I would have to, maybe some of you on the call know better the early universe constraints of the magnetic moment.
I think for this one, the stellar bound is more constraining, like globular clusters, like red giant cooling and stuff.
I see.
Yeah, I don't remember what numbers.
Yeah, but I think it's I think that's the best bound on it. But I'm not totally sure. It's not really something I look.
Oh, okay, right. Okay, thank you.
Yeah, my impression is my recollection, which is clearly like very fuzzy, is that the numbers are not here yet. But yeah, you're reminding me I should check what they are. I just know this number is the one that's in the PDG and is from Borx.
I see. Okay.
This guy up here.
Right. Thank you.
Also, can I ask quickly about this? The B minus L constraints. I don't know how.
It's kind of anticlimactic. A little bit anticlimactic figure.
This gap also is a bit intriguing. I mean, what do you know what happens to the beam dump constraints at like 1 MeV? Why they just cut off like that?
Because I think they are looking for visible decays. Let's see, right? So if it's like to the 2 electron.
Oh, I see.
Okay.
Really can't see stuff.
So. I think it's a kinematic constraint there.
Oh, okay. Yeah, that makes sense.
There was some work that was saying that there was a BBN constraint here that was in fact translating like Celine and Matt's paper to this their one on ineffective.
Yeah.
But I think that translation wasn't quite right. So I think that there is a constraint here from BBN, but not for the reasons. This was the